In this lecture, we'll discuss about carry look ahead adder. It is also a parallel adder. So in ripple carry adder and even in adder subtractor, in both, it need to wait for the carry. The next full adder can do addition only when previous full adder provide the carry. Okay, until it has to wait. If we can avoid this waiting, we can make this addition more faster. Okay, how can we avoid this waiting? If we know the carry value without waiting, then we no need to wait. But how can we know the value? Knowing that carry value without waiting is called as carry look ahead. Look means knowing or seeing the carry. Okay, ahead means before, until, without waiting. Okay, so in this lecture we'll see how we can know the carry value without waiting, so that we can avoid the waiting, so that we can make this addition more faster. So carry look ahead adder is the fastest adder than ripple carry adder and adder subtractor. Okay, right. So to know this logic, we need a full adder truth table. So this is the full adder truth table. You know how to do this truth table. So from this table you can observe two things. See here, a equal to b and a equal to b. When a equal to b, the output also same. A equal to b, 0 0 na, you got 0. Here 1 1 na, you got 1. So the point is when a equal to b, so here what I have to write, this is equal to, so when a equal to b, the carry out also same as a or b. Okay, a or b. Just a minute, it is saving. Okay, now let us observe another condition. When a not equal to b, this condition, what is the output? Whatever C in, that is coming to C out. See here, when a not equal to b, C out is becoming C in. So when the C out going to C, when the C in going to C out, from here it is going like that. That is called propagation. From here to here it is going like that. So this condition is called propagation. When propagation, when a not equal to b. When this is not going to out, that is called generation. It is not going here, it is getting some new other value, or it is generating some new other value, that is called generate. So this a equal to b condition is called generate, carry generate. This a not equal to b condition is called carry propagate. Okay, so here in this condition we can know what is the next carry value. Whatever C in, that will become C out. We can easily know, na? Okay, so how it is useful, I will tell you. Let us go to suppose this is ripple carry adder, this is C out, this is C in. Okay, so initially I am assuming I know my C in value, na, initial. So now to do this carry addition, we need to know C out also, C naught. Okay, so how to know C naught? Until this adder do addition and it is providing this one, it cannot know in normal carry locate adder, normal ripple carry adder. But if we know what is this value coming before only, it can do addition without waiting for it. Okay, so here can we know this value here, because here we know this value, this will be this one. If we know this value, we can know this value, so we can know this value. That is the logic there. Okay, if we know previous carry, we can know next carry, so that will be this carry. Okay, so this is one point we observed. And second point, we'll go to that. So in this condition, based on this, we able to know. In another condition, when a not equal to b, what is this output value? We know ab values, na, we only giving whatever ab value when both are same, that only we will get. It means see here in the circuit, suppose when I observe these two a0 b0 are same 0 0 or 1 1, same means here what I will get, same means 0 means 0 I will get, same 1 means 1 I will get. So I no need to wait until it providing carry. Based on this only I can know this value. If both are zeros, it will be 0, both are ones, it will be 1. When both are same, when both are different, we cannot know based on this. Based on this first carry only we can know further carries. But anyhow we able to know the carry values, na, without waiting. So that is called carry look ahead. So we are avoiding a waiting time, so we can make it more faster. So from this you understood carry look ahead logic, carry generate and carry propagate. Nothing but carry look ahead logic means generate and propagate logic. Okay, right. So now to design this logic circuit of carry look ahead adder, we need some equations, Boolean equations. So to get that equations, we need this diagram. This is not the carry look ahead adder. To get that equation, we need this diagram. What is this diagram? Full adder using half adders. I already explained how to do it. Full adder using half adders. So this is the symbolic and this is the logic diagram, same. Okay, so here previously when I explained this circuit, I assumed this a b. Now I assumed this as a I b I or ax bx, anything, no problem. So it will become, this will become the XR output, whatever propagate I told, this is the propagate. Whatever generate I told, this is the generate, this AND gate output. Okay, now this is carry in, I assumed as Ci. Okay, so this assumed as Si. Just we kept I to input values, that's it, input output values. Now this is the present carry. What this is next carry? If the present carry is I, next carry will become I plus 1. For this next carry, I plus 2, like that. So here you have to write I plus 1 and this equation we have to list out. We need this equation. So how can we determine this equation? See here what we coming we have to know. What we coming here we have to know. This is Gi. And here what we coming? First we have to know this, here Pi coming and Ci coming, C. So it will become Pi Ci, it will become Gi. So Ci plus 1 equal to Pi Ci plus Gi. That is the final equation. Okay, so now Ci plus 1 equal to Gi plus Pi Ci. This is the final equation. So in this equation, suppose in the carry look ahead adder also there is 4-bit adder, 8-bit adder, like that. If you want 4-bit adder, in this I place you have to substitute 0 to 3. 4-bit adder means I will be 0 to 3. So if I substitute I equal to 0, suppose 8-bit adder, if you take we implement 8-bit carry locate adder by cascading two 4-bit. We generally do 4-bit. That 4-bit will be like a IC. If you want 8-bit, you have to cascade two ICs of 4-bit. Okay, so this 4-bit is called a single stage or single level. If you take 8-bit, it will contain two level or two stage. One 4-bit is called one stage or one level. Okay, so now this whole design I am showing is for 4-bit. Based on this, you can do, if you cascade, you will get to higher order bit. Okay, so now 4-bit means I told I equal to 0 to 3. We have to get 4 equations. I equal to 0, I equal to 1, I equal to 2, I equal to 3. When we substitute whatever the equations we get, we have to list out those 4 equations, and by using 4 equations, if we draw a logic diagram, that will become carry look ahead adder. 4-bit carry look ahead adder. Okay, that will do. So first I substitute, this is the equation, same equation I taken, I substituted I equal to 0. Then how will it will become 0 plus 1. 0 plus 1 nothing but C1. C0 plus 1 nothing but C1. So this will become 0, no? I0, okay, G0, P0, C0. This will become 1, but these will become zeros because this is 1 because of plus 1. So this is one equation. Now I will substitute I equal to 2. Then it will become C2 equal to G1 plus P1 C1. Now in this C1 I can substitute this C1 equation. Now it will become like this. See, Z1 plus P1, this whole C1 I will write here. G0 plus P0 C0. Okay, right. Now I will substitute. So here I equal to 0, this is I equal to 1. I will remove just a minute. Okay. Now next, just a minute, it is saving. Okay, now I equal to 2 means C3 equal to G2 plus P2 C2. Again in this C2 we can substitute to previous C2 equation, then it will become C3, it will become like this. When I substitute I equal to 3, Z3 plus P3 C3. Again in this C3 I can substitute this whole equation, it will become like this. So finally we got 4 equations. Now if you do circuit with these equations, G1, P1, this final equations, it will look more complex. So what I am taking, I will take this equation, then this equation, instead of this and this both same, but it is simply looking simple now, I will take this to draw the circuit. You can do with this also. Okay, I have no space here, that's why I am using this one. Okay, and here I will take this one instead of this one. Here I will take this one instead of this one. Okay, right. So now how to draw logic diagram? Easy. So what are my outputs? C1, C1, C2, C3, C4. These are my outputs. So I will write outputs this side, C1, C2, C3, C4. So for C1, what I connected, see what is the equation of C1? C1 is equal to G0 plus P0 C0. For this P0 C0 I need one AND gate, and for G0 and this I need one OR gate. Okay, so I take an AND gate, I applied P0 C0, then I taken one OR gate, this AND gate output and this G0 I given to OR. This will become C1. Okay, I got C1. Now C2. How to get C2? Again C2 equal to P1 C1 AND operation. So this C1 I will give here like this, P1 C1 plus G1. this G1 I given, so C2 you will get. Now this will come here, this will go. Now this will come here, this will go. Okay, so you understood how to do this, okay, from the equations only. Okay, now here we have not mentioned what is P naught, what is G naught, and here we have not mentioned A value, B value and C in values. Okay, C in values we mentioned, but AB values we have not mentioned. Actually that is the numbers AB. If you don't give AB, it cannot do addition. So after doing this, what is this P naught? XR output, nothing but P naught equal to A naught XR B naught. What is this G naught? A naught and G naught. See in the circuit, P naught equal to A naught B naught, A naught XR B naught. G naught equal to A naught and B naught. Okay, naught means 0, I equal to 0 in that sense. Okay, because why I am telling I equal to 0, this equation came when I equal to 0 only, na, that sense. Okay, so P naught equal to A naught XR B naught, you connect, take one XR, give A naught B naught, XR output you give to P naught. Now take same A naught B naught you connect to, and that output you give to Z naught. Same you do for this, same you do for this, same you do for this, but here A1 B1, A2 B2, A3 B3. So here you are applying AB values. If I have 4 bit, that 4 bit I can get A0 to A3, 4 bit value A and 4 bit value B. 4 bit to A means A0 to A3, that bits I will give here. B0 to B3, those bits I will give here. Whatever initial carry Cin, this will be, it will become Cin. This is Cin. Okay, but here we write like C0 only. So you are giving AB values and Cin values. Okay, so because of this AB, P0 will come and C0 you are giving, so it will come, and because of this AB, Z0 will come, this 2 going, so this will come. If this is coming, it will come, 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 it will come. Addition will happen, 4 bit addition. It will happen very fast compared to that ripple carry adder and adder subtractor. Okay, so the advantage of carry locate adder is speed, more speeder, but the drawback is it is more complex than ripple carry adder or adder subtractor. Okay, so because we are interested in speed, even though it is complex, people using this only because people are interested about speed. They want to spend much money. Complexity means you need to more cost. Okay, I hope you understood carry locate adder. Okay, right.